right, good morning. Bit of a late start here, but that's okay. I'm gonna dive right in anyway, so there we go. Switched over and then we got to get my pop out. Keep forgetting. Okay, so this morning we're going to be looking at chapter 16 of crafting interpreters, and we're also going to take a look at, before I forget, we're going to look at the error message output that we were getting from where is it? How can I run this? There we go. Oops. Am I in the wrong? I am in the wrong directory. I got to set this up better so I can actually just run these however I want. Where we were expecting error messages to be a certain format, whether they are parse errors versus runtime errors, I think was the issue. And I need to look into that. But I want to start with chapter 16. I think that would be best. Because that's new stuff rather than hacking on and fixing old stuff. And new stuff is always shinier and funner than old stuff. All right, so let's get back to our working directory, lox bytecode. We should be clean. We are. Clippy should be happy. It is. All right, so now we're going to get into the scanner. So we just finished writing the beginnings of a VM. If we look at the VM code, we do have the main loop. We do have an optional debug trace execution thing, and then we implemented return statements. For those is an intermediate form of return. Right, we're going to get to a better return soon, hopefully. We do have the constant, which allows us to push things onto the stack. We have negate, which allows us to flip the sign of whatever's on the top of the stack. And then we added these 4 binary operators using this this technique here to go along with the technique in chapter 15, in which the author is using a macro instead of a function to do all the work. And we've got a function to do the work, but we're just passing in an anonymous function to actually get the work done here as op. So that's all that. But now we're going to look at scanning. And scanning, I think, is going to be very similar to, let's take a quick look at our lox AST source scanner, right? It's going to be very similar. We're going to probably do the same kind of thing where we have scan tokens, we match on the different token types. In fact, a lot of this is probably just going to be duplicate code, unfortunately. But let's go through it. As I say, our second interpreter, clox, has 3 phases: scanner, compiler, and virtual machine. So lox AST had the scanner, the parser, the resolver, and then the interpreter. So there are 4 different sections to deal with. This one has 3: scanner, compiler, which is different to the parser and resolver, right? And then the virtual machine, which executes the compile the code. A data structure joins each pair of phases. Tokens flow from the scanner to the compiler, and chunks of bytecode from the compiler to the VM. We begin our implementation near the end with the chunks and the VM. Right, so we have these chunks of bytecode already. They're called chunk. And here's all the opcodes for the chunks. Now we're going to hop back to the beginning and build a scanner that makes tokens. In the next chapter, we'll tie the 2 ends together with our bytecode compiler. Okay, so now we're going to ignore all of the VM and the chunks and everything like that. We're just going to scan and generate tokens. I admit this is not the most exciting chapter in the book. With 2 implementations of the same language, there's bound to be some redundancy. I did sneak in a few interesting differences compared to JLox's scanner. Read on to see what they are. All right, so spinning up the interpreter. Really? Interpreter? Now that we're building the front end, we can get clox running like a real interpreter. No more hand-authored chunks of bytecode. It's time for REPL and script load. Oh, okay. I see what they're saying. Okay. So we're going to, in main, I guess, we're going to add all this mess. We're going to rip out this stuff. We still need the VM, but we don't need any of these guys. And we're going to just check the args. So we're going to kind of steal locks AST, source main. I'm going to steal the code from here, right? We can just use the same kind of idea. Oh, and what I did was I created a separate locks executable thing. All right. So we have one prompt, and what they're doing is they've got REPL. So let's do that for arg1 REPL. We have run file. I'll just put that here. And the reason I did this in a locks thing is because that way I could have a single interpreter. Here we're going to just have a single VM. So let's do it this way. And this locks bytecode is what I'm calling this. Okay. And then we have the VM and the VM free. So we're not doing anything with those yet. And so now we have to write these functions, right? REPL, which is going to be similar to run prompt. Can we just steal this code? And we're going to have to change it because we no longer take a self parameter. We do need to grab standard IO. And probably buff read in, right? Let's see. We have standard out flush. Oh, right, for the prompt. We grab the line is empty, self run. We're not going to do that anymore. What are we going to call? Interpret line. And then we print that out again. Okay. A quality REPL handles input that spans multiple lines gracefully and doesn't have a hard-coded line length limit. This REPL here is a little more austere, but it's fine for our purposes. Oh, Supercuber, hi. How are you? Haven't seen you in a while. Hope all is well. The real work happens in interpret. We'll get to that soon, but first let's take care of loading scripts. All right, so let's do that. Run prompt, and we will have run file. Let's grab that. There's run file. I see your bytecoding already. Nice. Yeah. We this week I started Monday with the bytecode stuff. This does not take a self. It does take a path, and it returns an IO result. We read to string. So this read file is the read to string. So we don't need to do any of this read file business, right? Because all this is doing is allocating enough room for the file, reading the entire file into the buffer, putting a null at the end just to be on the safe side, I guess, and then closing the file. And that's all done in this read to string thing here. And then if it worked, if we call self run and it worked, then we have that. Okay, so what we're going to do is just call interpret buff. Right, and then we have to write interpret. Okay, so compile error is 65 and then runtime error is 70. So we can do that. Oh, we do have interpret in VM, right? Yeah, so we can call that directly on the VM. So we can pass the VM in. Let's create the VM here. And we can just pass it in. And this just takes a VM. Like that. Oh, mute. Right? And the same thing here. And then we just say VM dot interpret. VM dot interpret. Okay. And then and the result of this is going to be these things here. We don't generate these yet, but I did comment them out to get the thing to work. If we have interpret result, compile error, that's this thing here. And if we have a runtime error, Luna says, "Have my favorite uncle." I'm great, thank you. How are you? How's my favorite niece and or nephew and or other? So then we have okay, I guess we can exit at that point, right? With just 0. Oh, this should be interpret result. Right, those are the options. And this we can blow away. So interpret is supposed to take a chunk. So we actually need something more than just that, right? We can't just call interpret. We actually have to compile it first. So this isn't gonna build because interpret needs something more than just a string. Let's see when we get there. Right, so we did this. Real work happens in interpret. We'll get to that soon. So we read the file, execute the resulting string of lock's source code, then based on the result of that, we set the exit code appropriately because we're scrupulous tool builders and care about little details like that. We also need to free the source code because read file dynamically allocates it, right? Okay. Like a lot of C code, it takes more effort than it seems like it should, especially for a language expressly designed for operating systems. Yeah, one of the things he's not doing here, for example, is checking to see if open fails or ftl fails or rewind fails or anything like that. Nephew, hi. I managed to code movement with a tutorial. In what framework? Are you talking about like in Bevy? You've got moving working? Or some other framework? The code here is a classic trick to solve that. When we open the file, but before reading it, we seek to... Oh, right, yeah. So this, what they're doing here is trying to see what the file size is by looking at the file pointer after seeking to the end. Okay. Yeah, this is all C stuff. I'm not going to worry about C stuff. Oh, okay, yeah, okay. We're checking error messages or error returns out of fopen. We should also fseek, check errors. Malloc is important error check. Fread is also important error check. They all are. Oh, right here, he says it. Actually, the calls to fseek, ftl, and rewind could theoretically fail too, but let's not go too far off into the weeds. All right. Unity in C#. Nice. I played with Unity like years ago, but I never really got into it. So congrats on getting good on movement working. That's awesome. Even good old printf can fail. How many times have you handled that error? Never. I just cast it to void. Yeah, the fool doesn't check if printf failed. Says Supercuber. Yeah. All right. So opening the compilation pipeline. Okay, so now we're going to have this interpret function. We're replacing this. So instead of interpret taking in a chunk, all right, we're going to change this to take in a string. And we're going to call it source. And it's going to take a string. And now everything gets broken because we have to compile it first and then return and interpret. Okay, so we're not going to be able to run chunks anymore after we do this. I guess self-compile, source, and then interpret. Okay. Actually, we probably should just return whatever compile returns, right? Because it's going to error with compilation errors or whatever. I'm sure we'll get there. All right, if I do this, we should get warnings about unused functions. Oh, interpret result. Oh, did I forget args? I forgot args. Source, no. Lots AST. Source main. We have to grab this guy here. And REPL. Oh, I called it run prompt. And we don't have compile. What is this? Type's different. Oh, I have to pass an immutable thing here. Okay. Right, and compile doesn't exist. Expected reference to a string. Okay. That's easy to fix. and found expected reference. Okay, so now we're just down to this one compilation error that we're missing compile. We won't build the actual compiler yet in this chapter, but we can start laying out its structure. Okay, so for now the one function is declared like this. Oh, we're going to write it as a compiler, as a separate module. Does that make sense from our VM's point of view? I mean, I guess it makes sense from the point of view of code separation of concerns. So we can just say let, or we could just call, yeah, we can set let compiler equals compiler new, and then compiler compile. And then we'll just create a new compiler.rs, which has pub struct compile. Impl compile. I imagine we're going to have to add some stuff here, so that's why I'm going through this mess now. Pub fun new self, and then in main we have to add it as a mod. Oh, and then we have to add it here. Oh, compiler. And we don't have compile. Okay, so we're back to where we were. So, right, the compiler is going to have to call the scanner, so now we're going to have to write a scanner. Okay. Let's do that. Pub fun compiler. Oh, compile. Self and source. Can continue to be a string. And it's returning a void. That's interesting. You'd think that we would want to return an error if we had a compilation error. So we can say let scanner equals scanner new, and then scanner dot, and this is init scanner. So we'll just do that. And then we'll create a new file called scanner, which just creates a scanner. It looks like we have a start, a current, and the current line number. And these are just pointers to this into a string. So we're going to have a source, which is going to be a string. Oh, if we do reference to a string, that's going to be fun, isn't it? And then start is going to be an index into that, and then current is going to be an index into that. Actually, we want this to be a vec char, right? And we can just convert it directly from the string, and maybe line number, which is your size. Pub fun new. No, impl scanner. Now pub fun new. Self. Except we want to pass in the source, right? Source string. And this is going to be, source is going to be, source dot chars, I think. Iter collect. Can I do this? Vec of char. Maybe. And then start is 0, current is 0, and line is 0. Let's see if this builds. First I have to put it in main. I have to add it here. Use create scanner. And I need to pass in the source. Yeah, so private field, not a method. Oh, is chars already an iterator? It is. 32 warnings. Oh, yeah, because we're not using any of that stuff. Right. Okay. So now we have a vec of char. This allows us to index into start and current. I've got a feeling we're going to want to extract symbols out of this, so we're going to just have to build up the symbols. How did we do it? Oh, Diablo. Hi. You said crab. Here's a crab. Here's a crab for you. Okay. Oops. Over here. So I think we also did this in locks AST, source scanner, right? Where we pulled together tokens with substrings, with substring notation, right? So it was like a open bracket, yeah, using this. And then we had to iter collect on it to make a string out of it. So we're going to do the same thing in this scanner to pull the tokens together. It's a little less fancy than this is going to be, because this is just going to point directly into the source file, so we won't have to make copies of it. So it's going to be slower than the C version, but I can live with that. I now have crab as a service. Should definitely make that, right? So as our scanner chews through the user's source code, it tracks how far it's gone. Like we did with the VM, we wrap that state in a struct and then create a single top-level module variable of that type, so we don't have to pass all around the various functions. It would be nice if we could just start with, let's say, in source main, we have the string, or reference to the string. We could just pass in pointers, but then I think we'll have to mess around with lifetimes. And that gets, that'll go off the deep end, I think. Yeah, see, so start and current. So this will be the pointers into the symbol, right? And so we're going to do the same thing that we did in the locks AST. So a token at a time. In JLocks, when the starting gun went off, the scanner raced ahead and eagerly scanned the whole program, returning a list of tokens. This would be a challenge in CLocks. We'd need some sort of growable array or list to store the tokens in. We'd need to manage allocating and freeing the tokens and the collection itself. That's a lot of code and a lot of memory churn. At any point in time, the compiler only needs 1 or 2 tokens. Remember, our grammar requires only a single token of look ahead. So we don't need to keep them all around at the same time. Instead, the simplest solution is to not scan a token until the compiler needs one. When the scanner provides one, it returns a token by value. It doesn't need to dynamically allocate anything. It can just pass tokens around on the C stack. Unfortunately, we don't have a compiler yet that can ask the scanner for tokens, so the scanner will just sit there doing nothing. To kick it into action, we'll write some temporary code to drive it. All right, so in our scanner, what we'll do is not in our compiler, which I don't have yet. This compiles, right? Okay. So we're going to create the scanner. We're going to start a line number at -1. I guess so we can increment it. Where do we increment line? Oh, I see. If token line is not equal to line, then we're going to print out the new line. So that's what this is doing. Right. So what we can do is, instead of, because I want to use a usize, and you can't use -1, obviously, but what we can do is in our scanner, we can start line 1, right? Because it's going to be line 1 anyway, and just let mut line equals 0, and that way it'll be different. Okay, so ScanToken is actually passing back the struct token, which we don't have yet. I don't think we have struct token yet. Yeah. So we're going to have to create a token thing just like we did in locks AST. And that's actually that's a feature of C, right? Where you can pass back a struct and it doesn't do it. It doesn't make a copy of it. What it does is it puts this on the stack here and then passes a hidden pointer. You can't see it here because it's something that C does. It hands a hidden pointer to ScanToken and says, okay, write directly into this memory. How will we handle that in Rust is just by passing back a token. So ScanToken is going to scan a token. And then what we'll do is say loop. That's our four semi right there. So we can just say let token equals scanner scan token. And it's just going to take this source that it made a copy of already. So we're already making copies of things. And then we can just say if token, I guess we can make all these fields public. And we'll say prints bang token.line, just forward like that. And then we just say line equals token.line. Okay. Else print bang 1, 2, 3. Oh, there was a space after here. Okay. Just like that. So just like we did with the disassembler, it's the same code. And then print lin. This is going to be token type. Okay. The token length. Oh, and this is as the star parameter here. And then token start. Why do we need that? That %star as in the format is a neat feature. Usually you set the output precision by placing a number inside, right, using star. Oh, okay. So what would, yeah. So the token start is going to be pointing somewhere into the source string. And then the length is going to see how many characters are in that source. But we're just going to have the token. We're just going to have the name of the token directly in there. So instead of token length, we're going to have token type. I have to use token type like that, and then token, I'll call it start, but it'll just be a straight up string. And then if token t type is equal to token type EOF break. All right, and we don't have token yet. And we're going to have to add that at some point. This loops indefinitely. Each turn through the loop, it scans one token and prints it. When it reaches a special end of file token or error, it stops. So print 1 + 2 prints out 1 print, 131 print. I guess 31 is the token type for print. 21 is 1, 7 is plus, 21 is 2, 8 is semicolon, and then line 2, I'm guessing that's EOF. Wizard says token.lexeme. That is much better. Thank you. I think that's what we used in AST, right? All right. I'm sure we're going to get there at some point. Last empty lexeme on line 2 is the EOF token. The goal for the rest of the chapter is to make that blob of code work by implementing this key function. All right, so it's going to take the whole chapter to get this blob of code working. Raw index of the token type isn't exactly human readable, but it's all C gives us. Oh, yeah, so we can actually just print out the token type as a string, right? We don't need to do it this way. Although we can, I mean, because we can print out the enum using debug. We just don't have the length. I don't know. What would be a good length? 10? Does the question mark come before or after the 10? I don't know. This is going to all blow up. Yeah, okay. All right, so here's token. Oh, token is inside scanner in this one. Okay, why not? Scanner doesn't exist in my Git files yet. We can just put it here, pub struct token. And it's going to have a token type. A lexeme, which is going to be the string. The length we don't care about, and the line is the usize. Okay, so that's token. So that means we can actually eliminate the token here. Okay, and then we just have all of these guys in our token type enum. So pub enum token type. All right, I wanted to make these guys pubs, just for simplicity's sake. So we have left paren. This is going to take a while. You know what? Let's see if we can just grab it out of blocks AST, source token. Oh, it was token type. Yeah, okay. Sure, let's grab that. And just put it here. Okay. That was easy. And we did change assign and equals here. All right. So we hammered out the whole thing. So hopefully this is all there. Oh, I think I added break, right? That was one of the challenges, to add a break statement. All right, left paren, left brace, right brace, comma, blah, 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 blah. We have all those string is in there. I guess we got away with that. Token string, okay. Aside from prefixing all the names with token, since C tosses enum names into the top level namespace, the only difference is the extra token error type. What's that about? Oh, I don't have that. That's a new one. Very good. There are only a couple of errors that get detected during scanning: unterminated strings and unrecognized characters. In JLOX, the scanner reports those itself. In CLOX, the scanner produces a synthetic error token for that error and passes it over to the compiler. This way, the compiler knows an error occurred and can kick off error recovery before reporting it. The novel part in CLOX's token type is how it represents the lexeme. In JLOX, each token stored the lexeme as its own separate little Java string. If we did that for CLOX, we'd have to figure out how to manage the memory for those strings. That's especially hard since we pass tokens by value. Multiple tokens could point to the same lexeme string. Ownership gets weird. That's like that's the tagline for Rust, isn't it? All right. Instead, we use the original source string as our character store. Okay, so this is exactly what we're not doing here. We're actually going to, since we split out the string into vector chars so that we can parse it easier, we're going to build our own string. So we're going to do exactly this. As long as the main source code string outlives all of the tokens, everything works fine. I don't mean to sound flippant, we really do need to think about and ensure that source string, which is created far away over in the main module, has a long enough lifetime. That's why runFile doesn't free the string until interpret finishes executing the code and returns. Right? We could do this with lifetimes, and maybe that would be a good thing to do as a follow-on, is to try to rewrite this so we only have one copy of the source in memory, and just pass the lifetime of that source around. All right, we're ready to scan some tokens. Let's do it. So in our scanner, we have pub fun scan token. It's going to take a mutable reference itself and return a token. Scanner start equals scanner current. Okay. Not sure why we're doing that. If is at end. We're going to self make token, return self make token, token type EOF. Okay, and then we're going to return a self error token of unexpected character. Okay, that's a very simple scanner, isn't it? Since each call to this function scans a complete token, we know where we are. We know we are at the beginning of a new token when we enter the function. Thus, we set scanner start to point to the current character so we remember where the lexeme we're about to scan starts. Then we check to see if we've reached the end of the source code. If so, we return an EOF token and stop. This is a sentinel value that signals to the compiler to stop asking for more tokens. If we aren't at the end, we do some stuff to scan the next token. But we haven't written that code yet. We'll get to that soon. If that code doesn't successfully scan and return a token, then we reach the end of the function. That must mean we're at a character the scanner can't recognize, so we return an error token for that. This function relies on a couple of helpers, most of which are familiar from JLOX. So we have is at end. Function is at end. self returns bool. And here we're going to just check to see if scanner current is null, but this we're just going to see if current is equal to len of source. There we go. We require the source string to be good null terminated C string. If the current character is a null byte, then we've reached the end. To create a token, we have this constructor-like function. All right, so we have MakeToken. Are we modifying? No, so we can just take a immutable reference to self and return a token. And this says token. T-type is, oh, we have to pass in the token type. So we can just say T-type. And then lexeme is going to be a scanner. This is going to be source dot self source self start to self current. What was it? Iter something? I should have copied it. Source scanner. Oops. Really? Oh, there. Here it is. Yeah, iter collect. And then we have the line. It's going to be self line. That's the whole thing. Yeah, we don't have ErrorToken yet. And oh, because yeah, ErrorToken doesn't exist, we don't know it's going to return it. So, but here's ErrorToken. It uses a scanner start and current pointers to capture the token's lexeme, sets a couple of other obvious fields, and returns a token. It has a sister function for returning ErrorTokens. Self and message stir, and it returns a token. So T-type is going to be token type error. The lexeme is going to be message to string, and the line is going to be self line. So that's that. ScanToken still has an issue. Expected token. Oh, because I put a semi there. Okay. Perfect. Now we're up to 66 warnings. That's because we're not using any of these guys. What we have now is basically a working scanner for a language with an empty lexical grammar. Since the grammar has no productions, every character is an error. That's not exactly a fun language to program in, so let's fill in the rules. All right, so we're going to write an advance function for the scanner. Let C equals self advance, and it's just this down here, so let's add that right now. Mut self, and it returns a, I guess returns a char, why not? Self current plus equals 1. And we're going to return scanner self source of self current -1. Nice. Epic Lark says petition to make you implement a Mandelbrot set generator once you have all the bits in place to do so. Do you think locks can do that? I don't see why it wouldn't be able to do that. Yeah, I mean, okay. I'm game for that. We can make a text-based one, right? And then just pick different colors as different characters, right? Okay, does this check? This checks. Nice. Okay, so now we're going to go up here and switch on C. If it is this, then we're going to return self make token type left paren, and we're going to copy that for left brace, right brace, semi, comma, dot, minus, plus, slash, and star. This is all sounding very, very familiar, isn't it? Okay, so that's this, that's this, that's this, semi, comma, dot, minus, plus, slash, and star. All right, and then we just have to look for left paren. And this is going to become right paren, left brace, right brace, semicolon, comma, dot, minus, plus, slash, and star. Mizard suggests move the error token to underscore case and you can get rid of return. You're right. Yeah, if we do that. Good idea. Okay. We read the next character from the source code and then do straightforward switch to see if it matches any of Lox's one character lexemes. To read the next character, we use a new helper which consumes the current character and returns it. Right. I wrote that first. Okay. Next up are the two character punctuation tokens like bang equals and greater than equals. Each of these also has a corresponding single character token. That means when we see a character like bang, we don't know if it's right. Yeah, so we did the same kind of thing in JLox. So this is either going to be, oh right, we have to write the match function with an expected character. Okay, so what's the easiest way to do this? We can just say self MakeToken self dot isMatch, I think is what we called it. If it's equals, then it's token type bang equal, else token type bang. I'm just doing this on one line for now. I know it's going to get split out, but we need to handle it for equals, the less than, and the greater than. Like that. And then just bang equal. Is it equal, 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 less, and greater. Oh wait, equal equal is equals, and this is a sign, right? And now we need to write isMatch. Okay, so fn is match, mut self, expected char, returns bool. If self is at end, return false. If scanner current is not equal to expected, self source of self current not equal to expected, return false. Self dot current plus equals 1, true. Something is not happy. Oh, dang it. Yeah, okay. We have to do it in a fancier way here. We're gonna have to say let is EQ is equal to self is match equals, and then return this thing. Right, and then this. Oh, like that. Okay. Let's see if that works. Yep. Okay, so that seems to be the way to do it. Let's let me copy this line. I can just hit paste like that. this and like this. Q. Okay. This, paste this. Q. Go to that, put that. This will look better once it's formatted. EQ and that. Okay, that compiles. Now our scanner supports all of the punctuation-like tokens. Before we get into the longer ones, let's take a little side trip to handle characters that aren't part of a token at all. Whitespace. Our scanner needs to handle spaces, tabs, and new lines, but those characters don't become part of any tokens like seen. We could check for those inside the main character switch in ScanToken, but it gets a little tricky to ensure that the function still correctly finds the next token after the white space when you call it. We'd have to wrap the whole body of the function in a loop or something. Instead, before starting the token, we shunt off to a separate function. So this is here, where we set scanner start to scanner current, skip white space. Right, and then we have to write that. So skip white space. And it doesn't return anything. We're going to loop, and we're going to say char c equals peak, match peak, I guess. If it is a space or a return or a tab, then we're going to advance. Anything else is return. Although this says break. Oh, this is break from the switch, not from the for. Okay. And then we have to write peak. So peak just returns scanner.current. Okay. Fn peak, self, char, self, source, self, current. Doesn't like that. Oh. Huh. It doesn't, it says use a comment to end the match. Oh, you know what I need to do? I need to do this, right? And then probably this, maybe? And don't hit F1. Yeah, okay. A little messy, but it works. At least I hope it does. Right, so it's a sort of separate mini scanner loops consuming every whitespace character. We need to be careful it does not consume any non-whitespace characters. To support that, we use this. This simply returns the current character but doesn't consume it. The previous code handles all the whitespace characters except for new lines. So right, in new lines we're going to have to increment the line number. And advance. Okay, when we consume one of those, we also bump the current line number, right? Comments aren't technically white space. If you want to get all precise with your terminology, but as far as locks is concerned, they may as well be, so we skip those too. Diablo says petition rename his language to crab script. Okay, I will email Nystrom and see if he'd very kindly rename it crab script. All right. So we're still in skip whitespace where we're checking for comments. That's interesting. So we go here, and then we have to write a peak next. Then a comment goes to the end of the line. All right, so while self peak is not equal to a new line and not self is at end, self advance. Else return. All right, because we don't want to consume the slash. We don't want to consume this slash at all, so we just return as soon as we see the slash. Epic says we should abolish white spaces, and he wrote that all without white space. But he did put a new line at the end. So, all right. Yeah, we have to write peak next. So that's pretty straightforward. And then peak next, self, char, if is at end, self is at end. We obviously can't look at the next one because we're already at the end. This is just returning a null pointer. So we should return an option char here. None. Else. Sum. Self. Source. Scanner.current. Right. Self. Self current plus 1. And then up here we're going to just have to say if let. If peak next is sum of if let sum next equals self peak next. And unfortunately you can't do an and here. That would be nice. If next equals this. So unfortunately we have to have this nested if business. Okay, this is like peak for one character past the current one. The current character and the next one are both slash, we consume them, and then any other characters until the next new line at the end of the source code. Okay. So hopefully that checks. It does. We're down to 47. Epic says foiled by the need to actually send the message. Yeah. All right. So literal tokens. Okay, now we're getting into the numbers and the strings. Oh, Mizzard, yes, thank you. I keep forgetting that that's a feature of the language. If let some slash is equal to peak next. I keep forgetting about that. One of these days it's going to stick in my head. All right, so we're going to do strings next. So this is after all these make tokens. We can do a quote. We're going to say return string. So this will be just self string, comma. And then string looks like this, saying after skip white space. Okay. And this is going to return a token. While peak is not equal to quote and not is at end, if peak is new line scan. Okay, so we can have multi-line strings. One of the things that looks like it doesn't support is escaping quotes inside strings, so that you'd be able to, we put / quote in there, but all right. Epic says getting used to pattern matching thinking has been harder than learning to coexist with the borrow checker. Yeah, I mean, it's certainly a different way of having to think about the language, and the borrow checker tells you right away if something's going wrong. Whereas this little thing, the compiler is perfectly happy to let me do it. I don't know if Clippy would have caught that. That would be an interesting Clippy lint. While self peak is not equal to a double quote and not self is at end, if self peak is equal to a new line, then self line plus equals 1 and self advance. And then once we've advanced past if self is at end, error, self error token, unterminated string, else Add self advance and self make token, token type string. And I gotta spell this correctly. Like that. Epic says, any subversion aficionados in here by any chance? Anyone know what client certificate validation would suddenly stop working? I haven't used subversion in eons. Hopefully somebody knows. Maybe somebody on Toggle's Discord would know. They seem to be a pretty smart bunch. Oh, and I missed a closing brace somewhere. Usually tells me close to where it is. There it is, 176. Really? I thought I closed it right here. Oh, I put an extra paren here. Oops. There we go. All right, now down to 46. We're getting better. Similar to JLocks, we consume characters until we reach the closing quote. We also track new lines. Lock supports multi-line strings, and as ever, we gracefully handle running out of source code before we find the end quote. Main change here in CLocks is something that's not present. Again, it relates to memory management. In JLocks, the token class has a field type of object to store the runtime value converted from the little token's lexeme. Implementing that in C would require a lot of work. We'd need some sort of union and type tag to tell whether a token contains a string or double value. If it's a string, we need to manage the memory for the string's character array somehow. Instead of adding that complexity to the scanner, we defer converting the literal lexeme to a runtime value until later. In CLocks, tokens only store the lexeme, the character sequence, exactly as it appears in the user's source code. Later in the compiler, we'll convert that lexeme to a runtime value right when we are ready to store it in the chunk's constant table. Alright, doing the lexeme to value conversion in the compiler does introduce some redundancy. The work to scan the number literal is awfully similar to the work required to convert a sequence of digit characters to a number value. But there isn't that much redundancy. It isn't in anything performance critical, and it keeps our scanner simpler. So we could do it, right? Because we've got in our token, we have the lexeme. We could also stick in here an option number. Right, we could do that and just convert it here. And if the token type is a number, wherever the heck that went, here. Or we could actually just put the number directly in here. Right, we could say string, string, and number value. But we're not gonna, we'll just follow what they're doing. All right, so next up is numbers. Instead of adding a switch case for each of the 10 digits as a constructed number, we'll handle them here. So we could actually do it, right? We could say 0 to 9. Right, instead of doing this self number. Let's do it that way. This uses obvious utility function is digit. We finished scanning the number using this. Sure. While self peak is digit. I think that's in. Token self. I'm just going to do this because I want to see if it compiles. Make token type number. I think, oh, is digit doesn't exist? Oh, supplied 0 arguments, expected 1 argument. Oh, for the radix. Okay, yeah, 10. Okay. Look for the fractional part. If self peak is equal to a dot and self peak next. Oh boy. Because now I have to unwrap, but that might not have, that'll crash if The file ends with a dot. Is digit 10. I'm going to just do this for now, and then let me think about it. Advance. And then while self peak is digit 10, self advance. I think this will compile, yeah. And it's just this business here. We want to be able to check is at end. What does peak return if we're, oh, it just returns the current one. And advance will advance just moves up by 1. So we're not actually checking anywhere to see if we're at the end while we're parsing this number. Peak doesn't check. Peak next does check. So this could just blow right through. I wonder if this is a bug in here, or if I'm just missing something. Because isDigit doesn't check to see if we're at the end. I guess what'll happen is we'll hit the null character, right? And then isDigit will be false. This will be false here because it's going to be null. So we won't even enter this. And then we're going to make the token of the number and return it. So I guess it doesn't matter. So, Should this, oops. Should I change peak to check to see if we're at the end before trying to look at the current? All right, well, I'm going to leave it like this for now, and then when it fails, we'll fix it. All right, but this builds. The last batch of tokens are identifiers, both user-defined and reserved. This section should be fun. The way we recognize keywords in CLOCKSS is quite different from how we did it in JLOCKSS and touches on some important data structures. First, though, we have to scan the lexeme. Names start with letter or an underscore. Right, this is something we actually had to fix in our previous. So we just say this if, and I think it's just C, right? Yeah. If C dot is alphabetic or C equals underscore. Then we're going to say self-identifier, comma. I think we can do that. Yep. Okay, so is alpha is written for us here. So we're going to write identifier. So while self.peak is alphabetic. Oh, yeah, or underscore. What's the easiest way to do it? I guess we can say peak is alphabetic. And then we can do the same thing here. Self peak. Oh. Yeah. Okay. While self peak is alphabetic, alphanumeric. Right? Because we want alpha or digit, then advance. And I'll write that in a second. And then we're going to just say self make token identifier type. And right now it's just doing identifier. Okay. But first let me write peak is alphanumeric. And that's just going to take a self. And we're going to say let C equals peak, self peak. And we're going to return C is alphanumeric or C equals underscore. All right, and then we just have to write identifier type, which returns, oh, it doesn't take anything, it just returns a token type. That's weird. Expected rule, oh, right. Identifier. Still? Oh, this is an associated function, not a method. Right, we need to add the self. Okay, down to 44 warnings. Diablo says get one out of the source control, source management software. I use Git for this stuff, and I use Mercurial at work. So I use both of the ones that you consider being worse than Darks. I've never used Dark, so I don't know how good it is versus the other two. I guess that's not very exciting yet. That's what it looks like if we have no reserve words at all. How should we go about recognizing keywords? In JLox, we stuck them all into a Java map and looked them up by name. We don't have any sort of hash table structure in CLox, at least not yet. A hash table would be overkill anyway. To look up a string in a hash table, we need to walk the string to calculate its hash code, find the corresponding bucket in the hash table, and then do character by character quality comparison. Oh, we are going to build our own hash table from scratch. Huh. And of course that means we're going to cheat and use Rust's hash table. Right, so this is all of the keywords: print, return, super, this, and true, for and which. Right, we start at the root node and we work. Okay, so this is talking about trees and state machines. But do we need to do all this, or can we just cheat and use? We might as well do it this way, right? Just follow their pattern. I mean, we could just use a hash table, right? So we're going to say match scanner self. It's self scanner start. Why not just call peak? All right, match self source, self start. If it's an A, then we're going to say self check keyword 1, 2, ND token type token. Oh, it's just and. Right, and then we have C, E, I, N, O, P, R, S, V, and W. Okay, and then this changes, all these are ones. So we have 4, we have 3, we have 1, we have 2, another 1, 4, 5, 4, 2, and 4. Okay, so we have this ND thing, las for class, else for else, if for if, ill, oh, nil, okay, rint, eturn, Ooper. Oh, I missed one. This is just R for or. Rint. Etern. Ooper. R for var. And then while for while. And all these need to change. Class. Else. If. Nil. Or. Print. Return. Super. Var. And while. All right. These are the initial letters that correspond to a single keyword. If we see an S, the only keyword the identifier could possibly be is super. It might not be though, so we still need to check the rest of the letters too. In the tree diagram, this is basically a straight path hanging off the S. We won't roll a switch for each of these nodes. Instead, we have a utility function that tests the rest of the potential keywords lexeme. And that's check keyword. All right. Fn check keyword. Are we going to modify? Wouldn't we have to pass change current to point past? I would have thought that we would have to move the start so the next time we go through we actually get, but I don't see it doing that. I see int start, in length, const char star rest, and token type. So if the current minus the start equals the start plus the length, oh, we've already scanned? Is that it? We've already scanned it by the time we get to identifier type? Yeah, okay. So current is already passed. So we actually have now start to current is going to be the actual keyword. So now we're saying is if the length matches, and the strings match, then we're done. And that's just using a memory compare. So how are we going to do that? Here, self, start, usize, length, usize. And then what do we need? What are we using for rest? I don't see rest. Oh, here it is. Oh, this is the rest. I see. And then the token type is token type. And it's going to return a token type. All right, so how are we going to do this in... first, we can check the length, right? We can say if self current minus self start is not equal to start plus length. One plus two is, I was looking for 3. Okay, yeah, that makes sense. Return token type identifier. And now we need to compare the string. So we can pull the string out and do a string compare maybe. Where do I do it? Here. No? Here. Okay. In MakeToken. Let's put that down here. Keep jumping around too far. Here it is. So if our start minus, so we actually want to go start plus 1, right? Or start plus start. I'll let compare equals this. And then we can say if compare as stir equals rest. I don't know if this is going to work. And then we can say return type. Otherwise, we're going to just return this guy. I don't know if we actually need to check the length, right? We can just do the collection here and do it. And this is a premature optimization. For here, it makes sense because you're trying to do a memory compare and you want to make sure the length is equal. But here, we're going to just grab it, and then if this doesn't equal this, then I don't think we need to do that part. Does this check? It does not. Consider giving compare a type. And now this doesn't work. Oh, the rest of the patterns are invalid. So this just becomes token type identifier. Okay. All right, this compiles. Hopefully it's doing what I'm expecting it to do. And we use this for all the unbranching paths in the tree. Once we found a prefix that could only be one possible reserved word, we need to verify two things. The lexeme must be exactly as long as the keyword. If the first letter is S, the lexeme could still be sup or superb. The remaining characters must match exactly. Supar isn't good enough. If we do have the right number of characters and they're the ones we want, then it's the keyword. Then we return the associated token type. Otherwise, it must be a normal identifier. We have a couple of keywords where the tree branches again after the first letter. If lexeme starts with an F, it could be false, for, or fun. So we add another switch for the branches coming off of the F node. Okay. So that's this. If scanner current minus scanner start is greater than 1, then we're going to match on self source self start plus 1. Case A, self. Oh, I see why it would be simpler to just break out of it. Because we're going to have to add this for each one of these. All right. Check keyword 2.3 LSE token type false. Right, this FA LSE. Case O to 1 R as token type 4, and finally case U to 1 N. Fun. Otherwise, we do that, which is unfortunate because now we're going to need each one of these on each of these multi. Oh, there's only 2 of them. Okay, that's not too bad. Let's copy paste. Since we have the pattern down, and we can put it here and just change that to a T. This is H and this is R, and this becomes this, and this becomes true, and this becomes UE. Okay, that's it. A couple of nested switch statements. Not only is this code short, but it's very, very fast. It does the minimum amount of work required to detect a keyword and bails out as soon as it can tell the identifier will not be a reserved one. And with that, our scanner's complete. Okay, let's get it to compile first. Oh, what am I doing? The perils. All right, what did I do wrong here? Oh, I need an else. I need an else for this. Which means I can, and that's unfortunate because I need it down here too. And now this token type identifier is sprinkled all over the place. All right. We sometimes fall into the trap of thinking that performance comes from complicated data structures, layers of caching, and other fancy optimizations, but many times all that's required is to do less work. And I often find that writing the simplest code I can is sufficient to accomplish that. All right, so we have a scanner, I guess. It would be nice if the scanner could print something out. Let's see. We did have in our compiler. Yeah, it prints it out. So will this work? We have a bunch of errors because we're not using any of the VM things. We're not using chunks, but everything else seems to be okay. Scanner doesn't use length. I guess I don't need that. Huh. Why don't I need that? I'm doing self-start with self-current. Compare as stir. I guess I don't need it because we can get the length right from here. Or we pull this out, and if it's longer than whatever rest is, because this is the length of rest, right? So we don't actually need that. Let's try just running cargo run. We do have a prompt, print 1 + 2. So it was doing it, print number 1 ++ number 2 semicolon semicolon. But we went a little too far. So let's fix this bug. Line 280. We're trying to peek. Yeah, see, we're trying to peek past the end. Let's see where we are. And that's because we don't have our null terminated sentinel anywhere. And we should be able to skip white space, right? Yeah, we skip white space. Okay, so we're looking at, we are in skip white space and we're peaking. So, I don't know. Let's get this fixed and then we can I guess we should be checking is at end. Where does skip white space do that? Where is skip white space? Right here. Yeah, so it would just return null when we hit the end. I guess we can do that. Right, we can say if self is at end, we can just return null. Else. Right, and then we should be able to do this. Print 1 + 2. Yeah, ident this foo x + 1 times 45. Okay, all seems to work. We should be able to also run some locks through this, right? Cargo run locks ast bib 21. Yeah, that all seems to work. We can even get an EOF token at the end. Right? That looks good. I didn't do strings. Cargo run. Print. This is a string. Nice. Oh, it's including the quotes. Is that something we were oh, right. Yeah, he talked about that, where we would reinterpolate it afterwards. Let's take a look at, yeah, here's string right here. Yeah, it just says MakeToken. It doesn't adjust the start and the end to remove the opening and closing quotes. That's fine. All right, so I think we're good. I think we're good. Let's take a look at the challenges, and then I want to go back and poke around a little bit with the JLOX test suite. Many newer languages support string interpolation. Instead of string literal, you have some sort of special delimiters. Between these delimiters, an expression can appear. When the string literal is executed, the inner expression is evaluated. What token types would you define to implement the scanner for string interpolation? It was, yeah, so this would just be convert to a this plus this, right? And then this would just be an expression. Epic says they solved the subversion issue. About to set fire to everything with a Microsoft label on it. Okay. Keep a fire extinguisher handy. Several languages use angle brackets for generic and also have a right shift operator. This led to a classic problem in early versions of C++. This would produce a compile error because the angle brackets was lexed into a single right shift token, not two greater than tokens. Many languages, especially later in their evolution, define contextual keywords. These identifiers act like reserved words in some contexts, but can be normal user-defined identifiers in others. For example, await is a keyword inside an async method in C#, but in other methods you can use await as your own identifier. Huh. Name a few contextual keywords from other languages in the context where they are meaningful. Okay. Those are challenges I'm going to skip on. So we have this. We do have all the warnings. Git commit chapter 16, and chapter 16 is called Scanning on Demand. Normally I commit each subsection, but the subsections didn't compile, so I'll just leave it like that. And let's push that up. Git push. And let's say click peek here. There it is. Okay, scanning on demand. So with that, I have a few minutes. Let's take a look at how we're going to do this. So I want to have a difference between parse errors and runtime errors. If I run this in JLOX, I'll do it this way. cd build java semicolon let's do this and this and then // that. So it's saying line 2 here, error at this expected variable name. So that must be a parse error. So maybe the parse errors are meant to be like this. Println line this error at this. Right? Quote, comma, token not line and message. And then lox result runtime error is this. And we're going to do this business here. There we go. Okay. I'm going to get rid of this comma here because it's bugging me. All right. If I switch to mine now, I have to build it. We're still getting this error. So let's try running my code. And this is what's coming out of here. Oh, error at this. Oh, I'm missing the lexeme. And it should have a colon and the message. token Maxine, was it? I can't remember now. Or token as string. Yeah, okay. Let's see if this looks the same. Okay, that looks identical to the JLox version. So let's run Dart again. Oh, we got up to 28. Good. So 155 tests passed and 84 tests failed. I want to get past all the error message reporting problems and get to the actual bugs in JLox, because all this is now is a formatting issue currently. All right, so duplicate parameter. Let's compare. This is the output from here. We have already a variable with this name in this scope. And if we go to Java, which is here, okay. And the output is 65. Whereas my output is 0. Okay, that's no good. Because we are definitely reporting an error, but we're not getting an error. So what? This is going through this line here. And it shouldn't be. Oh, so I must be reporting a runtime error when it should be a parse error. So I think that's in the resolver. Yeah. Yeah, I'm reporting runtime error out of the resolver, and it should be a parse error. Let's see if that's the bug. Okay. Okay, so now that looks correct. All right, Dart. No, we're still getting, oh, expected error code 65 and got 0. Okay, so that's because, why? We are returning, we're reporting a part, oh, but we're just ignoring it and carrying on. Already. A variable with this name in the scope. Oh, declare doesn't return a result. Right, because this has had errors. So that's what we need to do is in source main. Where do we pull out the had error business here? Did we return that anywhere? Success. So in main, what we need to do is say if the parser had success, then this, else we had an error, right? And we need to exit with process standard process exit 65. So that's this when we run the file. So runtime error is 70, parser error is 65, I guess. We could just bail out here, right? Standard process exit 65. What we should do is have the parser just return a result. That would be a cleaner way of doing it. Oh, because I still need to okay. All right, let's build that. Oh, we're still getting 0. Okay, so that's not it. Oh, it's in the resolver. I did the wrong thing. Resolver success. Here, this is where we should do this. Okay, so this was okay like this. And this should be like this with this, right? Okay, let's try that. I had it in the wrong spot. Ooh, good. We got down to 37. We're at 168 tests passed and 71 tests failed. Okay, we're getting there. Expected return code 65 and got 70. So this is another issue where we have a parser error, but we're reporting a runtime error. All right, so this is using local and initializer. Let's compare mine. Right? Yeah, and this is another thing where we don't have the right output. If I go Java and put this test here. Yeah, okay. So it can't read a local variable. What line is that in? That's got to be in the resolver too, right? Read local. Yeah, runtime error. Why aren't I just using self.error? That's what I should be doing, self.error. Expert name, and then just this. Oh, because I want to return a LOX result. I guess we can just do this, because this will record the error, right? And then we'll be able to see that had error in there. Yeah, and then we should return a 65 at that point. No, I still have a problem. Let's see what my output looks like again. It's identical. Error at A, can't read local variable in its own initializer. Oh, I spelled it wrong. That would explain it. I-N-I-T-I-Z. There we go. I-N-I-T-I-A-L-I-Z-E-R. Okay. So hopefully that fixes that one. Oops. Dart. Nice. We're down to 41. Okay. 169 tests passed. We're still at 70. Okay. And now we have a few more errors here. Unexpected character. Error at B. Expected close paren after arguments. All right. Let's do this one more and then we'll call it a stream. So this is what I output with error 65. And if we go back to this guy, this is their output. Oh. We get 2 lines of output, and it is a 65. Okay. So we see line 3 error, unexpected character, and the error at B, expect close paren after arguments. So where do we get unexpected character? It's in the scanner. We're just calling error with the line number. And all this does is save the line number issue. It doesn't report the actual error. I mean, it doesn't report the second line here of expected something after arguments. Where's that? Expect. Is this coming out of the scanner and this is coming out of the parser? Or maybe this one is meant to error, self error, parse error, token message. Maybe the parse error is supposed to have these double informational lines. And the other one should be called resolve errors when we get the other one, because I don't want to break the resolve errors that we just fixed. But the only unexpected character comes out of here. Okay. All right. This one I'll take a I guess I'll break here. We got some more issues fixed. Git status, git add source, git commit, some more test suite error message fixes. Because I want to get to the point where we're not parsing error messages, we're actually finding bugs in the interpreter. All right, let's push that sucker up and call it a stream. All right, is anybody doing Rust? Just me. I'm the only one listed on this Rust thing. Oh well. Let me refresh this and see if there's anybody else we can raid. Nope. Okay. That's too bad. All right, so with that, I'm going to leave you. Tomorrow, we're going to look at the next chapter in this book, Compiling Expressions, chapter 17. And then, if there's time, again, we will continue fixing up the EST test suite. All right. Have a great rest of your day, everyone, and I will see you tomorrow.